Close your eyes and imagine the softest deep within your body, in the peaceful darkness of every cell, there exists a language more ancient than any words ever spoken aloud. This language has no sound. It needs no voice. It writes itself in molecules so small that millions could dance on the head of a pin. Yet this silent alphabet holds the instructions for everything you are. The curve of your smile. The color that pools in your eyes. The rhythm your heart learned before you took your first breath. Scientists call this language DNA. But tonight, as you rest in the gentle embrace of sleep, think of it as poetry written in light. For simple letters repeat themselves in endless, beautiful combinations. A for adenine. T for thymine. G for guanine. C for cytosine. Like notes in a lullaby, they arrange themselves in patterns that have been singing the song of life for billions of years. Picture these letters floating through your body like fireflies on a warm summer evening. They cluster together in long, spiraling chains. Each chain twists and dances with its partner, forming the famous double helix that you might have seen in pictures. But this is not just a picture. This is happening inside you right now, as you breathe, as you listen, as you slowly surrender to rest. Your DNA stretches through your cells like the most delicate thread. If you could pull all the DNA from just one cell and lay it straight, it would reach 6 feet long. Now imagine that this thread, thinner than spider silk, contains enough information to fill a library. Every cell in your body carries this complete library. Your skin cells know the instructions for your eyes. Your heart cells remember the recipe for your bones. This is the miracle that scientists are learning to read more clearly each day. They peer into this molecular library with tools that can see individual letters. They trace the sentences that spell out brown hair or blue eyes. They follow the paragraphs that determine whether you might be tall or short, whether you will love the taste of cilantro or find it bitter. But here is what makes this story even more beautiful. You are not just a copy of this ancient text. You are a unique edition, never written before and never to be written again. Your mother gave you half of her library, and your father shared half of his. When these two collections joined together, they created something entirely new. You. Some of your letters came from grandparents you never met. Others traveled to you from ancestors who lived centuries ago. Mixed within your personal alphabet are echoes of people who laughed under different skies, who loved in languages you have never heard. You carry their stories forward, written in the same four letters that have guided life since the very beginning. The scientists who study this language often work late into the night, just as you are settling into sleep. They use machines that can read thousands of letters in minutes. They compare your unique text to others, looking for the sentences that might cause illness or the words that bring extraordinary gifts. In laboratories around the world, they are learning to understand what each paragraph means, what each chapter controls. This understanding brings both wonder and responsibility. For the first time in human history, we can read the instruction manual of life. We can spot the tiny typos that sometimes cause pain. We can see the beautiful variations that make. Like careful librarians, scientists are developing tools that can change single letters. They can correct a misprint that might cause suffering. They can adjust a word that might prevent a child from seeing clearly or hearing music. These tools work with incredible precision, changing only what needs to be changed, leaving the rest of the beautiful story untouched. The most precise of these tools has a name that sounds almost musical, CRISPR. It acts like molecular scissors guided by a wise librarian. It can find one specific letter among the billions in your genetic library. It can cut out that letter and replace it with another. All of this happens in the realm of the impossibly small, in the quiet space where your cells dream. Tonight, as you rest, your cells continue their gentle work. They read from your genetic library constantly, following the instructions written there. They build new proteins like tiny construction workers following blueprints. They repair damage like careful editors fixing worn pages. They divide and grow, each new cell carrying a perfect copy of your unique story. You are both the reader and the story being read. You are the library and the visitor who wanders its halls. Your genetic letters shaped you before you were born, and they continue to guide the miracle of your existence every moment of every day. Yet you are more than just your DNA. You are the experiences that color those genetic instructions. You are the choices that dance with your inherited possibilities. As sleep draws you deeper into rest, feel the quiet activity of your cells. Feel the ancient letters spelling out the poetry of your existence. Feel the gentle rhythm of a language that connects you to every living thing on Earth. Tomorrow, in laboratories around the world, scientists will continue learning to read this language more clearly. They will ask deeper questions about how these molecular letters might be gently edited to prevent suffering and enhance human flourishing. In the soft darkness of your resting mind, imagine a pair of scissors so small they could cut moonbeams. These scissors exist not in dreams, but in the real world of molecules and cells. They dance through the corridors of DNA with grace that would make ballerinas weep with envy. Scientists call these molecular scissors CRISPR. The name sounds like autumn leaves crackling underfoot, but it stands for something much longer and more complex. What matters tonight is not the complicated name, but the beautiful simplicity of what these scissors can do. They can find one specific letter in the vast library of your genetic code. They can cut it out with surgical precision. They can replace it with something better. This discovery began not in a laboratory, but in the most unexpected places on Earth. Deep beneath the ocean floor, where no sunlight has ever touched, bacteria have been fighting an ancient war. Viruses attack them constantly, trying to hijack their genetic machinery. To survive, these tiny creatures develop their own defense system. They learn to cut the invading viral DNA into harmless pieces. For millions of years, this molecular battle raged in silence. Bacteria would capture pieces of viral DNA and store them like mugshots in a genetic photo album. When the same virus attacked again, the bacteria would recognize it instantly. They would send out their molecular scissors to slice the invader apart before it could cause harm. Scientists studying these ancient bacteria discovered something remarkable. The same system that protected bacteria from viruses could be programmed to edit any DNA they wanted. It was like finding a master key that could unlock any genetic door. The molecular scissors didn't care whether they were cutting viral DNA or human DNA. They simply went wherever they were guided. Picture these scissors as the most precise instruments ever created. They can navigate through the 3 billion letters of human DNA and find the exact spot they need to edit. Imagine trying to find one specific word in a library containing every book ever written. Now imagine doing this while blindfolded. This is the level of precision these molecular tools achieve every day. The scissors work with a guide, like a seeing-eye dog for the molecular world. This guide is made of RNA, a cousin of DNA that knows exactly where to go. Scientists can program this guide to search for any genetic sequence they choose. The guide RNA floats through the cell until it finds its perfect match. When it locks into place, it calls the scissors over to make their precise cut. The cutting happens in a moment too brief to measure. One instant, the DNA strand is whole. The next, it has been severed at exactly the right spot. But these molecular scissors are not destructive. They are healers. They create space for something better to take the place of what was removed. What happens next feels almost magical. The cell's own repair system rushes to fix the break. Sometimes, the scientists let the cell repair itself, removing unwanted genetic instructions entirely. Other times, they provide a template, a genetic patch that contains the correct information. The cell's machinery carefully stitches this new information into place. This process happens inside living cells as you sleep. In laboratories around the world, scientists guide these molecular scissors through genetic landscapes more complex than any map. They edit the genes of mice to understand how specific letters control behavior and health. They modify bacteria to produce life-saving medicines. They work with plant cells to create crops that can feed more people while using less water. Each edit requires patience and wisdom. The scientists must understand not just where to cut, but what will happen after the cut is made. They study the ripple effects that spread outward from each change. They test their edits thousands of times before moving forward. They work with the reverence of people who understand they are touching the source code of life itself. The beauty of CRISPR lies not just in its precision, but in its gentleness. Unlike older genetic tools that were crude and unpredictable, these molecular scissors work with surgical elegance. They can change a single letter without disturbing the rest of the genetic sentence. They can correct a typo without rewriting the entire paragraph. As this technology has grown more refined, scientists have discovered they can do more than just cut and paste. They can turn genes on and off like dimmer switches. They can guide the scissors to specific locations without cutting at all, using them as molecular delivery trucks to bring helpful proteins exactly where they're needed. The same tools that bacteria developed to defend themselves against ancient viruses now offer hope for treating human diseases that have caused suffering for generations. Scientists are learning to edit the genes that cause blindness, allowing children to see clearly for the first time. They are correcting the genetic mistakes that lead to sickle cell disease, freeing people from lives of pain. But perhaps most remarkably, these edits can be made not just in the cells of people who are already alive, but in the cells that will become future children. This possibility brings both extraordinary hope and profound questions. When we edit the genetic letters that will be passed down to the next generation, we are writing messages that will echo through time. The molecular scissors continue their precise dance tonight, in laboratories where dedicated scientists work by the light of microscopes and computer screens. They move with the careful steps of people who know they are choreographing the future of human health and possibility. In this quiet moment before sleep takes you completely, consider the ancient bacteria that first developed these molecular tools millions of years ago. They could never have imagined that their simple defense system would one day offer humanity the power to gently edit the very essence of life. Tomorrow, we will explore the garden where human traits bloom like flowers, and discover how these molecular scissors might help us tend that garden with wisdom and care. Close your eyes and imagine the most beautiful garden you have ever seen. Now imagine that this garden exists inside you, growing from the genetic seeds planted before you were born. Each flower in this inner garden represents a different part of who you are. The color of your hair. The shape of your smile. The way your mind processes the world around you. Some flowers bloom early and obviously. Your eye color announced itself when you were just months old. The dimples that appear when you laugh were carved by genetic instructions written in your DNA long before you had anything to smile about. These traits are like the bold sunflowers that catch everyone's attention as soon as they push through the soil. Other flowers take their time. Your adult height is still growing from genetic seeds that won't finish blooming until you are fully grown. The way your voice will sound when you speak as an adult remains hidden in genetic buds that haven't opened yet. These traits are like the patient perennials that wait for exactly the right moment to reveal their full beauty. In this garden of traits, some flowers grow from single genetic seeds. If you can roll your tongue into a tube, thank one specific gene that learned this trick from one of your parents. If you have attached earlobes instead of free-hanging ones, a single genetic instruction made that decision for you. These simple traits follow clear patterns, like roses that always grow red when planted from red rose seeds. But most of the flowers in your genetic garden are far more complex. Your intelligence doesn't bloom from one genetic seed, but from hundreds of different influences working together like a carefully planned wildflower meadow. Your personality grows from the interaction of countless genetic threads, woven together with all the experiences life has given you. Consider the flowers that bloom in your mind. Some people's brains are wired to see patterns in numbers as clearly as you might see shapes in clouds. Others have minds that can hold entire symphonies, playing each instrument in perfect harmony inside their thoughts. Still others have the gift of understanding exactly how another person feels, as if emotions have visible colors that only they can see. These mental flowers grow from genetic soil that science is only beginning to understand. Your working memory might bloom from genetic seeds scattered across multiple locations in your DNA. Your ability to focus deeply or to switch quickly between different thoughts grows from a garden plot that includes dozens of genetic influences. The remarkable thing about this inner garden is that it's constantly changing. New flowers can bloom throughout your entire life. The genetic instructions for learning are always active, always ready to help new skills and knowledge take root. Your brain continues to grow new connections, like a garden that keeps expanding its borders every season. Scientists studying this genetic garden have discovered something wonderful. Many of the traits that make you special are not determined by single genetic flowers, but by the way different plants interact with each other. Your creativity might bloom brightest when genetic seeds for curiosity grow next to seeds for persistence. Your kindness might flourish when genes for empathy share soil with genes for emotional strength. This complexity makes the garden beautiful, but it also makes it challenging for scientists to understand. When they look at simpler traits like eye color, they can trace clear paths from specific genes to visible results. But when they study complex traits like intelligence or musical ability, they find gardens within gardens, each one influencing the others in subtle ways. Some flowers in your genetic garden are more delicate than others. The genetic instructions that guide your immune system work like careful gardeners, protecting you from diseases that could damage other plants. When these protective flowers are strong and healthy, your whole garden thrives. When they struggle, the entire system needs extra care and attention. Scientists are learning to identify which genetic seeds are most important for growing healthy, flourishing gardens. They can now look at a person's DNA and predict with growing accuracy which flowers are likely to bloom brightest. They can see which plants might need extra water or better soil to reach their full potential. This knowledge brings both exciting possibilities and gentle responsibilities. If scientists can identify genetic seeds that might produce flowers of suffering, genes that lead to serious diseases or disabilities, they might also be able to replace those seeds with healthier alternatives. The molecular scissors we learned about can edit the garden at the genetic level, removing thorns and planting more beautiful blooms in their place. But editing this garden requires wisdom deeper than any scientific knowledge. Each flower serves a purpose, even if that purpose isn't immediately obvious. The same genetic variations that can cause challenges in one environment might provide unexpected strengths in another. The genes that make some people more sensitive to pain might also make them more sensitive to beauty. Your genetic garden is uniquely yours, but it's also connected to every other human garden on Earth. The flowers blooming in your traits share ancestral seeds with gardens growing in people from every continent and every culture. We are all variations on the same basic garden plan, each one beautiful in its own way. As you rest tonight, feel the quiet growing happening inside you. Feel the genetic flowers that are still blooming, still becoming. Feel the traits that make you wonderfully, irreplaceably you continuing to unfold like morning glories opening to greet the dawn. Your garden grows in the intersection of the genes you inherited and the life you have lived. Every day adds new experiences to the soil where your traits take root. But what happens when scientists gain the power to plant entirely new seeds in this garden, or to edit the ones that are already growing? What occurs in that sacred moment when a new life begins, carrying genetic modifications forward into an uncertain future? In the quiet darkness before dawn, imagine the moment when two drops of morning dew touch and become one. This gentle joining happens in a space so small it exists beyond the reach of your eyes, yet it marks the beginning of every human story ever told. This moment is conception. One cell from your mother, carrying half of her genetic library, meets one cell from your father, carrying half of his. They dance together in a ballet of molecules and merge into something entirely new. You. Complete with your own unique combination of genetic instructions, different from anyone who has ever lived or ever will live. For the first few days after this magical joining, you existed as just a handful of cells. Each one identical to the others, each one carrying the complete blueprint for everything you would become. These early cells are like seeds that haven't yet decided what kind of tree they will grow into. Scientists call them stem cells, and they hold within themselves the potential to become any part of your body. In these first precious days, something remarkable happens. The cells begin to make choices. Some decide they will become your heart, others your brain. Some choose to become the bones that will support you, others the skin that will protect you. It's as if each cell listens to quiet whispers in the genetic wind and follows the path that calls to it most strongly. This is the window of time that scientists find most fascinating and most hopeful. During these early days, when you were just a cluster of cells smaller than the period at the end of this sentence, your entire future was still fluid. The genetic instructions were there, but they hadn't yet been locked into permanent form. It is here, in this sacred space between potential and reality, that the molecular scissors we learned about can work their gentlest magic. When scientists use CRISPR to edit genes in these early cells, they are not changing a person who already exists. They are making quiet adjustments to the blueprint before construction begins. Think of it like editing a recipe before you start cooking. If you notice the recipe calls for too much salt, you can change it before you begin mixing ingredients. But once the cake is baked, you cannot remove the salt without starting over completely. The early embryo is like that uncooked recipe, still open to gentle improvements. Scientists working in this delicate realm must move with the reverence of people handling something infinitely precious. They work with embryos created in laboratory dishes, in the warm, controlled environment that mimics a mother's body. Under powerful microscopes, they guide the molecular scissors to exactly the right location in the genetic text. The editing happens in moments too brief to imagine. One instant, a genetic letter that might cause lifelong suffering is part of the DNA. The next instant, it has been replaced with a letter that will allow health to flourish instead. The embryo continues growing, completely unaware that its future has been gently reshaped. But this power brings questions that science alone cannot answer. When we edit the genes of these early cells, we are making changes that will last not just for one lifetime, but for all the generations that follow. The children born from edited embryos will pass those changes to their own children, and those children to theirs, in an endless chain reaching into the future. This is different from other kinds of medical treatment. When doctors give medicine to someone who is sick, the effects end when that person's life ends. But when scientists edit the genes of an embryo, they are writing messages that will echo through time. They are making decisions not just for one person, but for all of that person's descendants. Some of the changes scientists can make are clearly beneficial. They can remove genetic letters that cause terrible diseases like Huntington's disease, which slowly destroys the brain. They can correct the genetic mistakes that lead to sickle cell anemia, where misshapen blood cells cause waves of excruciating pain. These edits prevent suffering that has plagued families for generations. Other possible edits exist in a more uncertain space. Scientists are learning to identify genetic variations that might make someone more intelligent, stronger, or more resistant to certain diseases. But these traits are complex, growing from the interaction of many genes rather than just one. Editing them requires wisdom that goes far beyond technical skill. The scientists who work in this field often describe feeling the weight of history on their shoulders. They know they are among the first humans ever to hold this power. Every choice they make creates precedents that will guide future generations. Every edit they perform teaches the world something new about what is possible and what is wise. In laboratories around the world, these careful researchers work with embryos donated by families who cannot have children naturally. They practice their techniques, learning to make edits with ever greater precision. They study what happens when specific genes are changed, building a library of knowledge that grows larger each day. The embryos they work with will never become babies. They exist only to teach scientists how this technology works and how it might be improved. But each lesson learned brings us closer to a time when genetic editing might help real families have healthy children who would otherwise suffer from inherited diseases. Some countries have decided that editing human embryos crosses a line that should not be crossed. Others allow research but forbid bringing edited embryos to full development. A few have created careful guidelines that permit genetic editing only for the most serious medical conditions. The world is still deciding together what wisdom looks like in this new age of genetic possibility. As you rest tonight, consider the mystery of your own beginning. You started as two cells that found each other in the darkness and chose to become one. You grew from a cluster of cells so small they could fit inside the eye of a needle, yet they carried within themselves the instructions for your eyes, your heart, your capacity to love and dream and wonder. You were shaped by genetic letters written over millions of years of evolution, combined in a pattern that had never existed before and will never exist again. You are both ancient and utterly new, carrying forward the biological wisdom of countless generations while expressing it in your own unique way. But now, for the first time in human history, we have the power to gently edit those ancient letters before a new life begins its journey. The question that keeps scientists awake at night is not whether we can do this, but whether we should. And if we do choose to edit the genetic foundations of future children, how do we decide which changes heal and which ones cross the line into something more complex and morally uncertain? In a quiet hospital room in China, on a November day in 2018, two baby girls opened their eyes to a world that had never seen their like before. They looked perfectly ordinary, with tiny fingers that grasped at air and voices that announced their arrival with the universal cry of newborns. But hidden within their cells, written in letters too small to see, was something extraordinary. Their genes had been edited before they were born. These twin girls, given the names Lulu and Nana to protect their privacy, were the first humans ever born with intentionally modified DNA. In the months that followed, a third baby would join them, another child whose genetic code had been gently altered in those crucial early days of development. Together, these three children became living symbols of a new chapter in human history. The scientist who made this possible worked quietly in his laboratory, using the molecular scissors we have learned about to make precise changes to embryonic cells. His name was He Jiankui, and he believed he was giving these children a gift. He edited a gene called CCR5, removing genetic letters that would have made the children vulnerable to HIV infection. HIV is a virus that has caused immense suffering around the world. It attacks the immune system, leaving people defenseless against infections that healthy bodies can easily fight off. The scientist knew that some people are born with natural changes to the CCR5 gene that make them resistant to HIV. He wanted to give this same protection to children whose parents carried the virus. In his mind, he was performing an act of prevention, like giving a child a vaccination before they encounter a dangerous disease. The edits he made were small, changing just a few genetic letters out of the billions that make up human DNA. The children would grow up never knowing they had been modified, living normal lives with the added benefit of resistance to a devastating virus. But the world did not see his actions as a quiet gift. When he announced what he had done at a scientific conference, the news spread like ripples across still water, growing larger and more powerful as they traveled outward. Scientists, ethicists, and ordinary people around the globe responded with a mixture of wonder, concern, and sometimes anger. Many scientists felt he had moved too quickly, crossing a line that the global community had not yet agreed should be crossed. They worried that he had not done enough testing to ensure the edits were safe. They questioned whether the benefits justified the risks of making changes that would be passed down to future generations. Others were concerned about the way he had worked in secret, without the open discussion and careful oversight that such groundbreaking research typically requires. Science works best when it happens in the light, with many minds contributing wisdom and many eyes watching for potential problems. His solitary approach went against these time-tested principles. Yet underneath the controversy, these three children continued to grow and develop like any other children their age. They learned to walk and talk, to laugh and play. They were not science fiction creatures or laboratory experiments, but real human beings with families who loved them and futures full of ordinary possibilities. Their existence raised questions that had never needed answers before. If we can edit genes to prevent disease, where do we draw the line between healing and enhancement? If we can protect children from HIV, should we also edit genes that might make them smarter, stronger, or more beautiful? Who decides which genetic changes are medical necessities and which are simply preferences? The scientific community responded to these questions by calling for a pause. Researchers around the world agreed that no more gene-edited babies should be created until better safety protocols could be developed and clearer ethical guidelines could be established. They wanted to learn from what had happened, to study the long-term effects, and to have the difficult conversations that should have happened before the first edited children were born. Meanwhile, the scientist who created this situation faced serious consequences. He lost his job and was eventually sentenced to prison for conducting unauthorized medical practices. The scientific community made it clear that his approach, however well-intentioned, was not the careful, transparent way that such research should proceed. but the children themselves remained at the center of ongoing research and care. Scientists continued to monitor their health and development, looking for any signs that the genetic edits might have unexpected effects. So far, they appear to be growing up normally, showing no obvious differences from other children their age. Their blood cells carry the edited genes that should protect them from HIV, though thankfully they have not yet been exposed to the virus to test whether this protection actually works. The edits appear to have been passed successfully to their cells throughout their bodies, just as the scientist intended. However, detailed analysis of their DNA has revealed that the edits were not as precise as hoped. The molecular scissors made some unintended changes alongside the intended ones, creating genetic patterns that don't exist naturally. Scientists are still studying what these extra changes might mean for the children's long-term health. These 3 children have become unwitting ambassadors for a technology that could reshape the future of human health. Their existence proves that genetic editing of human embryos is not just theoretical possibility but practical reality. They have opened a door that cannot be closed, though the world is still deciding how carefully that door should be guarded. As they grow older, they will likely never know the weight of history they carry in their cells. They will go to school, make friends, fall in love, and perhaps have children of their own. If they do become parents, they will pass their edited genes to the next generation, making their modifications a permanent part of the human genetic story. Scientists continue to study their development with the dedication of gardeners tending precious seedlings. Every milestone they reach, every sign of health or concern, teaches the world something new about what it means to edit the human genome. Their lives have become a long-term experiment in the possibilities and responsibilities of genetic modification. Their story reminds us that behind every scientific breakthrough are real people living real lives. These children did not choose to be part of history, but they carry within their cells the hopes and fears of a world grappling with new power over the very essence of life. Tonight, as you rest in the gentle darkness, think of these 3 children sleeping peacefully in their beds, their edited genes quietly working alongside all the other genetic instructions that make them human. They are growing up in a world that is still learning what their existence means. As they continue to develop and thrive, the scientific community watches and learns, preparing for the day when genetic editing might move from experimental exception to carefully regulated medical practice. But that future requires wisdom about more than just technical precision. In hospitals around the world, there are children whose bodies carry genetic letters that spell out stories of pain. Their DNA contains ancient typos, small mistakes that have been passed down through generations like whispered secrets that grew darker with each telling. Tonight, we visit the quiet spaces where scientists work to rewrite these painful stories with gentler endings. Consider a little girl named Sarah, whose real name we keep private to protect her family's peace. When she was born, her genetic code contained a single letter change in a gene called hexa. This tiny alteration, smaller than a grain of sand in a vast desert, condemned her to a disease called Tay-Sachs. Without treatment, children with this condition slowly lose their ability to see, hear, and move as harmful substances build up in their brain cells. For generations, families like Sarah's could only watch helplessly as this genetic mistake stole their children away piece by piece. Parents would hold their babies close, knowing that each smile, each laugh, each moment of recognition might be among the last. The genetic letters that caused this suffering seemed as permanent as words carved in stone. But the molecular scissors we have learned about can change even these deeply carved patterns. Scientists can now edit the hexa gene, replacing the harmful letter with the correct one. They can do this directly in the child's own cells, teaching the body to produce the missing protein that prevents the deadly buildup. This type of genetic editing feels different from the controversial changes made to embryos. When scientists fix genes in children who are already suffering, they are clearly acting as healers. They are not enhancing human capabilities or creating advantages that don't naturally exist. They are simply correcting mistakes that cause pain. The process happens quietly, almost like magic. Scientists take some of the child's blood cells and bring them to the laboratory. There, surrounded by the gentle hum of machines and the focused attention of researchers, the molecular scissors find their target. They locate the single incorrect letter among the billions in each cell's genetic library. They cut it out with surgical precision and replace it with the letter that should have been there all along. Once the cells are corrected, they are carefully prepared and returned to the child's body through a simple injection. These edited cells travel through the bloodstream like tiny messengers carrying good news to every part of the body. They settle into the bone marrow, the soft tissue inside bones where new blood cells are born, and begin their healing work. Over the following weeks and months, the corrected cells multiply and spread. They gradually replace the cells that carry the genetic mistake. The child's body slowly learns to produce the missing protein, and the harmful substances that were building up in the brain begin to clear away like morning fog lifting from a peaceful valley. For children like Sarah, this treatment can mean the difference between a life cut tragically short and a future full of possibilities. The genetic editing doesn't give them superpowers or unusual advantages. It simply allows them to have what most people take for granted, healthy cells that function as they should. Scientists are using similar approaches to treat other genetic diseases that have caused suffering for generations. They edit genes to help children with sickle cell disease, where misshapen blood cells cause waves of excruciating pain. They correct genetic letters in children with severe immune deficiencies, giving their bodies the ability to fight off infections that would otherwise be fatal. Each treatment requires months or years of careful preparation. Scientists must study each child's unique genetic pattern to understand exactly what needs to be fixed. They must test their editing techniques in laboratory cells before using them in real patients. They must monitor each child carefully to ensure the edits work safely and effectively. The families of these children often describe the treatment as a miracle, but the scientists know it is something more complex and more beautiful than magic. It is the result of decades of patient research, countless hours of careful experimentation, and the gradual accumulation of knowledge about how life works at its most fundamental level. These healing applications of genetic editing face fewer ethical questions than the enhancement possibilities we considered earlier. When a child is suffering from a genetic disease, most people agree that correcting the problem is both medically appropriate and morally right. The goal is not to make the child better than normal, but to give them the chance to be normal at all. Yet even these clearly beneficial uses of genetic editing require careful oversight. Scientists must ensure that the treatments are as safe as possible, that the benefits outweigh any risks, and that families understand what the procedures involve. They must work with ethics committees and regulatory agencies to make sure each treatment meets the highest standards of medical care. The children who receive these treatments become part of a new chapter in medical history. Their healthy cells carry the evidence that genetic diseases once considered incurable can now be treated. Their growing bodies demonstrate that the molecular scissors can work not just in laboratory dishes, but in the complex environment of living human beings. As these children grow up, they will carry forward the benefits of their genetic edits while living otherwise normal lives. They will go to school, make friends, and pursue their dreams just like any other children. The only difference will be the absence of suffering that once seemed inevitable. Tonight, as you rest in the comfortable darkness, think of these children sleeping peacefully in beds around the world. Their cells work quietly through the night, producing the proteins they need, clearing away the substances that once threatened their health. They dream ordinary dreams, unaware that they are living proof of medicine's growing power to heal at the genetic level. But even as scientists celebrate these clear victories against genetic disease, they must grapple with more complex questions about human diversity and difference. What happens when the line between correcting disease and eliminating natural variation becomes harder to draw? Imagine a garden where every flower blooms in exactly the same way. The petals would be identical, the colors uniform, the fragrances indistinguishable from one another. Such a garden might seem orderly, but it would lack the breathtaking diversity that makes natural gardens so beautiful. Human minds, like flowers in nature's most magnificent garden, bloom in countless different ways. Some minds process the world with extraordinary attention to detail, noticing patterns and textures that others miss entirely. Some brains create connections between ideas in ways that seem almost magical, finding relationships where others see only randomness. Some people experience emotions with such intensity that they can feel the joy or sadness of strangers as if it were their own. These differences in how minds work have names that scientists use to describe them. Autism. ADHD, dyslexia, synesthesia. But these clinical labels, while useful for doctors and researchers, cannot capture the full richness of human neurodiversity. They are like trying to describe a symphony by naming only the instruments, missing the beautiful music that emerges when different sounds combine. Consider the mind of someone with autism, whose brain might focus on details with laser-like precision while finding social interactions as complex as navigating a foreign city without a map. This person might notice that a bird song has 17 distinct notes, or remember exactly how shadows fell across a room 3 years ago. Their mind works differently, not defectively. Many people with autism describe their experience as living in a world designed for minds that work differently from theirs. Social conversations happen too quickly, with unspoken rules that seem arbitrary and confusing. Bright lights feel like needles against their skin. Unexpected sounds crash through their consciousness like thunderclaps. Yet these same sensitive minds often excel at recognizing patterns, solving complex problems, and creating art that reveals beauty others cannot see. Scientists studying the genetics of autism have discovered something fascinating. The traits associated with autism appear to be controlled not by single genes, but by hundreds of genetic variations working together like instruments in an orchestra. Some of these variations increase sensitivity to sensory input. Others affect how the brain processes social information. Still others influence attention and focus. Here lies one of the most profound questions that genetic editing technology forces us to consider. If we can identify the genetic patterns that contribute to autism, should we edit them out? Is autism a condition to be cured, or a form of human diversity to be celebrated and supported? The autistic community itself is deeply divided on this question. Some people with autism experience significant challenges that limit their independence and cause them distress. They might welcome genetic interventions that could ease their difficulties with communication or reduce their sensitivity to overwhelming sensory experiences. Others argue passionately that autism is not a disease to be cured but a different way of being human. They point to the unique gifts that autistic minds bring to the world: breakthrough scientific discoveries, innovative technological solutions, artistic creations that reveal new ways of seeing reality. They worry that editing out autism might rob humanity of perspectives that have contributed immeasurably to human progress. Similar questions arise around other forms of neurodivergence. People with ADHD often struggle with traditional educational systems and work environments that demand sustained focus on single tasks. But these same minds frequently excel at creative problem solving, thinking outside conventional boundaries, and maintaining high energy for projects that capture their interest. Dyslexia makes reading traditional text a slow and sometimes frustrating process. Yet many people with dyslexia show exceptional abilities in spatial reasoning, creative thinking, and seeing the big picture that others might miss while focusing on details. Some of history's most innovative entrepreneurs, artists, and inventors have been dyslexic. The genetic patterns underlying these conditions are complex webs involving hundreds of genes, each contributing small effects that combine in ways scientists are only beginning to understand. This complexity makes genetic editing far more challenging than correcting single-gene diseases like the ones we explored in our previous chapter. But even if the technology eventually becomes capable of making such complex edits, the question remains, should we? When we consider editing genes associated with neurodivergence, we are not just treating medical conditions. We are potentially altering fundamental aspects of human cognitive diversity. Some researchers suggest that the genetic variations associated with autism, ADHD, and other neurodivergent conditions might have evolutionary advantages. Perhaps the intense focus of autism provided benefits when humans lived in small groups where attention to detail could mean the difference between finding food and going hungry. Maybe the high energy and creativity of ADHD helped our ancestors adapt quickly to changing environments. If this is true, then editing out these genetic patterns might reduce the cognitive diversity that has helped humans thrive in diverse environments. We might create a world of minds that all work in similar ways, losing the creative friction that comes when different types of thinking interact and combine. Yet we cannot ignore the real challenges that neurodivergent individuals face in a world often designed without their needs in mind. Some people with autism experience severe anxiety and communication difficulties that limit their ability to form relationships or live independently. Some children with ADHD struggle so profoundly with attention that they cannot succeed in school despite their intelligence and creativity. The path forward likely lies not in choosing between acceptance and intervention, but in finding ways to support neurodivergent individuals while preserving the diversity they bring to human experience. This might mean editing genes only in cases where the challenges are severe and the individual or their family chooses intervention. It might mean focusing more on changing environments to be more inclusive rather than changing minds to fit existing environments. As genetic technology advances, families facing these decisions will need support from scientists, ethicists, and the neurodivergent community itself. They will need information about both the challenges and the gifts associated with different ways of thinking. They will need time to consider not just what is technically possible, but what is wise and compassionate. Tonight, as you rest in the quiet darkness, consider the magnificent diversity of human minds. In bedrooms around the world, autistic children are dreaming in patterns and colors that neurotypical minds cannot imagine. Children with ADHD are processing experiences with an intensity and speed that generates ideas like sparks from a fire. Each mind contains unique combinations of genetic instructions that have been refined over millions of years of evolution. Each represents a different solution to the puzzle of human consciousness and creativity. But as we gain the power to edit these ancient genetic patterns, we must also consider how our choices today will echo through generations not yet born, shaping the minds that will inherit tomorrow's world. Picture a stone dropped into the center of a perfectly still lake. The ripples spread outward in perfect circles, growing wider and wider until they reach shores you cannot see. When scientists edit the genes of an embryo, they are dropping a stone into the lake of time itself. The changes they make will spread through generations like ripples through water, touching lives that have not yet begun. This is the profound responsibility that comes with editing what scientists call the germline. These are the genes that will be passed down from parent to child, child to grandchild, in an unbroken chain reaching into a future we cannot fully imagine. Unlike the genetic edits that help sick children by changing only their own cells, germline editing creates changes that become part of humanity's permanent genetic heritage. Think of your own family tree, stretching backward through time. Your great-grandmother's eyes live on in your cousin. Your grandfather's musical talent echoes in your sister's voice. Genetic traits flow through families like underground rivers, sometimes hidden for generations before bubbling up in unexpected places. When we edit embryonic genes, we are redirecting these ancient streams. The 3 children we met earlier, the first humans born with edited genes, carry changes that will travel with them for their entire lives. If they have children of their own, roughly half of those children will inherit the edited genes. Those grandchildren who carry the modifications will pass them to half of their children. The genetic changes will spread through their family lines like seeds carried on the wind. In one sense, this is simply how genetics has always worked. Every parent passes genetic variations to their children. Natural mutations occur constantly, creating new genetic combinations that have never existed before. Evolution itself depends on this endless mixing and changing of genetic instructions. Genetic editing simply makes this process more intentional and precise. But intention brings responsibility. When genetic changes happen naturally, they are the result of chance encounters between molecules, random events that no one controls or directs. When scientists edit genes, they are making deliberate choices about which traits will be passed to future generations. They become guardians of genetic changes that will echo through time. Consider what this means for a family whose child receives edited genes that protect against a terrible disease. Not only is that child protected, but some of their descendants will inherit the same protection. A single genetic edit could shield multiple generations from suffering that has plagued their family line for centuries. But the ripples can spread in unexpected directions. Genes often influence multiple traits, like musicians who can play several different instruments. A genetic change designed to prevent one problem might create subtle effects elsewhere in the body. These secondary effects might not become apparent until the edited genes have already been passed to children and grandchildren. Scientists study these possibilities with the patience of archaeologists examining ancient artifacts. They test genetic edits in laboratory cells and animal models, trying to predict how changes might affect not just the immediate traits they want to modify, but all the other genetic systems that might be touched by the ripples. Sometimes the secondary effects of genetic changes are beneficial. The same genetic variation that causes sickle cell disease in people who inherit it from both parents provides protection against malaria in people who inherit it from just one parent. Nature often creates these genetic trade-offs, where the same DNA letters that cause problems in one situation provide advantages in another. This complexity means that genetic edits that seem clearly beneficial might have consequences that only become apparent years or decades later. A change that protects against heart disease might subtly influence brain development. An edit that enhances immune function might alter how the body responds to certain medications. The web of genetic interactions is so intricate that even small changes can create unexpected patterns. Future generations will inherit not just the genetic edits themselves, but also the responsibility of understanding what those changes mean. Children born with edited genes will need to know their genetic history when they make their own medical decisions. They will need to understand how their modified genes might affect their health, their children's health, and their children's children. This creates a new kind of genetic literacy that will become increasingly important as more families include edited genes. People will need to understand not just their natural genetic inheritance, but also the intentional changes that scientists made to their family's genetic code. They will become stewards of genetic modifications they did not choose but will carry for their entire lives. The responsibility extends beyond individual families to entire communities and cultures. If genetic edits become common, they could gradually change the genetic landscape of human populations. Some genetic variations might become more common while others slowly disappear. These shifts would happen over many generations, but they could eventually alter the fundamental genetic diversity that has allowed humans to adapt to different environments and challenges. Scientists working in this field often describe feeling the weight of future generations watching over their shoulders. Every genetic edit they make is a message written to descendants they will never meet. Every choice about which genes to modify and which to leave and change becomes part of humanity's evolving genetic story. Some research groups are working to develop ways to make genetic edits reversible, like pencil marks that can be erased if they prove problematic. Others focus on creating genetic switches that could turn edited genes on or off depending on changing circumstances. These approaches might allow future generations more control over the genetic changes they inherit. The children who carry the first intentionally edited human genes are growing up unaware that they are living bridges between humanity's genetic past and its engineered future. Their cells contain both the ancient genetic wisdom accumulated over millions of years of evolution and the precise modifications made by human intention and skill. As they play and learn and grow, their edited genes work quietly alongside their natural ones, integrated so seamlessly that no one could tell the difference without sophisticated laboratory tests. They are proof that genetic editing can become part of the continuous story of human genetic variation. Tonight, as you rest in the gentle darkness, consider the invisible threads that connect you to ancestors you never knew and descendants you will never meet. Your genes carry forward the accumulated wisdom of countless generations, and someday they may carry the careful modifications that science makes today. But with this power to edit the genetic instructions of tomorrow comes the need for wisdom that transcends any single generation's understanding or values. In the quiet hours when most of the world sleeps, committees of thoughtful people gather in conference rooms around the globe. Scientists sit beside philosophers. Doctors share tables with religious leaders. Parents who have lost children to genetic diseases listen to advocates for disability rights. Together, they wrestle with questions that have never needed answers before. What limits should guide the power to edit human genes? These conversations happen in the soft glow of conference room lights, over cups of cooling coffee and stacks of research papers. The people in these rooms know they are writing the rules for a technology that could reshape the future of human health and possibility. They approach their work with the gravity of architects designing bridges that must carry the weight of generations. The first boundary they consider is perhaps the clearest, the line between healing and enhancing. Most people agree that using genetic editing to treat serious diseases represents compassionate medicine. Correcting genes that cause childhood blindness or fatal metabolic disorders falls clearly on the healing side of this line. These edits restore normal function rather than creating advantages that exceed typical human capabilities. But as you move away from clear-cut medical emergencies, the boundary becomes softer, like the place where ocean meets shore. What about editing genes that increase the risk of common diseases like diabetes or heart disease? These genetic changes don't guarantee illness, but they make it more likely. Should preventing probable future suffering count as healing, or does it cross into enhancement territory? Consider height, a trait influenced by hundreds of genetic variations. Most people would not call short stature a disease requiring treatment. Yet for some families, genetic variants that lead to extremely short height can cause social difficulties and health problems. When does editing for height serve medical needs, and when does it become cosmetic enhancement? The committees grapple with even more complex questions about intelligence. Scientists have identified genetic variations that influence cognitive abilities, though the effects are small and the interactions complex. If parents could edit their child's genes to prevent intellectual disability, most would consider this appropriate medical care. But what if the same technology could boost a child's IQ from average to exceptional? Different countries have reached different conclusions about where these boundaries should be drawn. Some nations have banned all genetic editing of human embryos, declaring the technology too risky and ethically complex to permit. Others allow research but prohibit bringing edited embryos to full development. A few have created carefully regulated pathways that permit genetic editing for serious medical conditions. The United Kingdom established one of the first regulatory frameworks for genetic editing research. Their scientists can study genetic modifications in human embryos for up to 14 days, the point when the embryo would normally implant in the womb. This research helps them understand how genetic editing works and what safety concerns might arise, but it stops well before any edited babies could be born. China, where the first gene-edited babies were created, responded to that controversy by creating stricter regulations and heavier penalties for unauthorized genetic editing. The scientist who created those children was sentenced to prison, and new laws require extensive oversight and approval for any genetic editing research involving human embryos. Some countries focus their regulations on the distinction between editing genes in adult patients versus editing embryos. They permit genetic modifications that affect only the treated individual, like the therapies for children with genetic diseases that we explored earlier. But they prohibit edits that would be passed to future generations, viewing heritable genetic changes as crossing an ethical line that current science is not wise enough to cross safely. Religious communities bring their own perspectives to these discussions. Some faith traditions see genetic editing as a form of healing that aligns with their values of reducing suffering and caring for the vulnerable. They view the technology as a tool that humans can use responsibly to fulfill their role as stewards of health and well-being. Other religious voices express concern about genetic editing, particularly when it involves embryos. They worry about the implications of intentionally altering human genetic inheritance, viewing it as overstepping appropriate human authority. Some emphasize the value and dignity of human life in all its natural variations, including conditions that others might seek to edit away. Disability rights advocates add crucial perspectives to these conversations. Many point out that genetic editing might be used to eliminate conditions that they do not view as diseases requiring cure. They worry that widespread genetic editing could reduce acceptance and support for people who live with genetic differences, creating a world less welcoming to human diversity. Indigenous communities often approach these discussions from yet another angle, emphasizing the connections between genetic heritage and cultural identity. They raise questions about who owns genetic information and how editing decisions should be made within communities that view genetic inheritance as part of their collective rather than individual heritage. The conversations in these committee rooms are slow and careful, like gardeners planning where to plant trees that will grow for generations. Members share personal stories that illuminate the human faces behind abstract ethical principles. A parent describes watching their child suffer from a genetic disease. A person with a disability explains how their condition has shaped their unique perspective on the world. These diverse voices gradually weave together recommendations that try to balance innovation with caution, hope with humility. They create guidelines that aim to maximize the healing potential of genetic editing while minimizing risks and respecting different values and beliefs about human nature and medical intervention. Most of these groups agree on several core principles. Genetic editing research should be transparent, conducted openly with appropriate oversight rather than in secret. Any clinical applications should prioritize safety, with extensive testing and monitoring to ensure that benefits outweigh risks. The technology should be accessible rather than available only to wealthy families, preventing genetic advantages from becoming another form of inequality. They also generally agree that genetic editing should not be used for purely cosmetic purposes or to create capabilities that exceed normal human ranges. The goal should be helping people achieve typical health and function rather than creating genetic advantages that divide humanity into enhanced and unenhanced populations. But significant disagreements remain about where exactly these boundaries should be drawn and how they should be enforced. Some committee members favor permissive approaches that give individual families broad freedom to make genetic editing decisions. Others prefer restrictive frameworks that limit genetic editing to only the most serious medical conditions. As these conversations continue around the world, they create a patchwork of different approaches to governing genetic editing. Some regions become destinations for families seeking genetic modifications that are prohibited in their home countries. Others become centers of research that advances understanding while maintaining strict ethical boundaries. The wisdom these committees seek is not the kind found in textbooks or laboratories. It is the deeper wisdom that comes from bringing together diverse perspectives and experiences, allowing different voices to challenge and refine each other's thinking. Tonight, as these thoughtful people continue their quiet work in conference rooms lit by the glow of laptop screens, they carry the hopes and concerns of parents, patients, and communities around the world. They seek to create boundaries that are firm enough to prevent harm yet flexible enough to allow healing. But even as they work to establish these guidelines, the science itself continues to advance, creating new possibilities that will require new conversations and new wisdom. In the soft darkness of your dreams tonight, imagine standing at the edge of a vast library filled with books that have no words yet. Each empty page waits for stories that have never been told, futures that exist only as whispers of possibility. This is where we find ourselves now, holding the molecular scissors of genetic editing, wondering what tales we should write in the genetic code of tomorrow. The scientists working in laboratories around the world are like careful scribes, preparing their pens and choosing their words with infinite care. They know that every genetic edit they make becomes part of a story that will unfold across generations. Every molecular change they craft today will help determine whether future chapters speak of health or illness, of challenges overcome or burdens carried forward. Some of the stories they are preparing to write seem as clear as morning light. In research centers across the globe, teams are developing genetic therapies for diseases that have caused suffering for thousands of years. They are learning to edit the genes that cause Huntington's disease, a condition that slowly steals away memory and movement. They are perfecting techniques to correct the genetic mistakes that lead to cystic fibrosis, where thick mucus clogs the lungs and makes every breath a struggle. These healing stories feel like natural extensions of medicine's ancient mission to reduce suffering and restore health. When scientists use genetic editing to prevent a child from inheriting a fatal disease, they are writing chapters of relief and hope into family histories that have known too much sorrow. But beyond these clear cases of healing, the future pages grow hazier, filled with possibilities that shimmer like mirages in the distance. Scientists are beginning to understand how genetic variations influence traits like intelligence, creativity, and emotional resilience. They are mapping the complex networks of genes that determine how tall we grow, how quickly we age, and how our minds process the complexities of the world. This growing knowledge raises questions that feel both thrilling and unsettling. If we can edit genes to prevent intellectual disability, should we also edit them to enhance intelligence beyond typical human ranges? If we can correct genetic factors that contribute to depression and anxiety, should we also modify the genes that influence personality traits like shyness or assertiveness? Imagine a future where parents routinely edit their children's genes not just to prevent disease, but to give them advantages in life. Children might inherit edited genes that make them taller, stronger, more resistant to aging, or more capable of learning complex skills. These genetic gifts could accumulate over generations, creating families and communities with increasingly enhanced capabilities. Such a future might bring remarkable benefits. Genetic editing could eliminate hereditary diseases that have plagued humanity for millennia. It could enhance human resistance to new diseases, helping our species adapt to changing environmental challenges. It could even extend healthy human lifespan, allowing people to contribute their wisdom and experience to the world for longer periods. But this same future also carries shadows that make thoughtful people pause and consider carefully. If genetic enhancements become common, they might create new forms of inequality more profound than any that have existed before. Children born to families who can afford genetic editing might possess advantages that go far beyond what education or opportunity alone can provide. The gap between enhanced and unenhanced humans could become a chasm that divides society in ways we can barely imagine. Enhanced individuals might live longer, think more clearly, resist disease more effectively, and adapt more readily to new challenges. Over time, they might become so different from unenhanced humans that they constitute separate branches of the human family tree. Some scientists envision a more gradual and inclusive future where genetic editing becomes as accessible as vaccination programs today. In this gentler vision, the benefits of genetic modification would be shared broadly, helping all of humanity become more resilient and healthy rather than creating new forms of privilege and disadvantage. They imagine genetic editing being used primarily for clearly beneficial purposes, eliminating genetic diseases, enhancing resistance to cancer and heart disease, and perhaps extending the healthy years of human life. These modifications would be available to everyone, regardless of economic status, ensuring that genetic improvements serve to lift up all of humanity rather than dividing it. Other researchers focus on developing genetic modifications that could help humans adapt to environmental challenges. As climate change alters the world's ecosystems, genetic editing might help people thrive in new conditions. Modifications could enhance tolerance for heat, improve efficiency in using scarce resources, or increase resistance to new diseases that emerge as the planet warms. The most visionary scientists even consider how genetic editing might help humans venture beyond Earth. Space travel exposes the human body to radiation, low gravity, and other stresses that our genes never evolved to handle. Genetic modifications could help future space travelers remain healthy during long journeys to other planets, expanding the reach of human civilization across the cosmos. Yet for all these grand possibilities, the most immediate future of genetic editing likely lies in quieter applications. Scientists continue to refine techniques for treating genetic diseases in children who are already born. They work to make these therapies safer, more effective, and more accessible to families around the world. They are also developing new ways to edit genes temporarily, creating modifications that last for months or years rather than lifetimes. These approaches could provide therapeutic benefits without making permanent changes to human genetic inheritance. They offer a middle path between leaving genetic diseases untreated and making irreversible modifications to the human genome. The regulatory frameworks we explored earlier continue to evolve as the science advances. Countries that once banned genetic editing research are beginning to allow carefully controlled studies. Nations that permitted research are starting to consider clinical applications for the most serious genetic diseases. International organizations work to coordinate these efforts, ensuring that advances in one country benefit people everywhere and that the wisdom gained from each success or setback is shared broadly. They seek to prevent genetic editing from becoming a luxury available only in certain parts of the world, while also ensuring that the technology develops safely and ethically. As the technology matures, the questions shift from whether genetic editing is possible to how it should be used wisely. The molecular scissors grow ever sharper and more precise. The understanding of genetic systems becomes deeper and more nuanced. The ability to predict and control the effects of genetic modifications improves with each experiment and each clinical trial. Tonight, as you rest in the gentle embrace of sleep, consider that you are living through one of the most remarkable chapters in human history. You are witnessing the moment when our species first gained the power to intentionally guide its own genetic evolution. The children being born today will grow up in a world where genetic editing is not science fiction but medical reality. They will face choices about their own genetic modifications and those of their children that no previous generation ever had to consider. But perhaps the most important question is not what we can do with genetic editing, but what we should do, and how we can ensure that this powerful technology serves the flourishing of all life rather than the advantage of only a few. Imagine watching a master gardener tend an ancient forest. She does not reshape every tree or redirect every stream. Instead, she works with the natural patterns she finds, removing obstacles that prevent healthy growth, guiding young saplings toward sunlight, and occasionally planting new varieties that will thrive in the existing ecosystem. This is how the wisest scientists approach genetic editing, not as conquerors of nature, but as careful gardeners working within evolution's grand design. For billions of years, evolution has been conducting its own vast experiment in genetic modification. Random changes in DNA letters create new variations in every generation. Most of these changes disappear quickly, proving harmful or unnecessary. But some provide advantages that help organisms survive and reproduce. These beneficial variations spread through populations over countless generations, slowly refining the genetic instructions that guide life. This natural process has created the remarkable diversity of life we see today. It has crafted the eagle's keen eyesight, the dolphin's echolocation, and the human brain's capacity for language and abstract thought. Every gene in your body has been tested and refined by millions of years of evolutionary selection, kept because it contributes something valuable to survival and flourishing. When scientists edit genes, they are joining this ancient conversation between genetic variation and natural selection. But instead of waiting for random mutations to occur and then watching over generations to see which ones succeed, they can make intentional changes based on their understanding of how genes work. They can accelerate beneficial modifications that might otherwise take thousands of years to develop naturally. Consider how evolution naturally protects some people from genetic diseases. Over many generations, natural genetic variations have emerged that provide resistance to conditions like sickle cell anemia, Huntington's disease, and various forms of cancer. These protective variations exist in human populations because they arose randomly and then proved their worth by helping people live healthier lives. Scientists studying these natural protective variations can learn to replicate them through genetic editing. Instead of waiting for random chance to provide a child with genes that resist a particular disease, they can intentionally introduce those same protective changes. They are not creating something unnatural, but rather giving children access to beneficial variations that already exist within human genetic diversity. This approach respects the wisdom embedded in evolution while using human intention to distribute that wisdom more fairly. A child whose family has never carried natural resistance to a genetic disease can receive the same protection that other families inherited through the lottery of natural variation. Sometimes evolution solutions are more complex than human scientists initially understand. Genes that cause problems in one context may provide hidden benefits in another. The same genetic variation that leads to sickle cell disease when inherited from both parents provides malaria resistance when inherited from just one parent. Evolution preserved this seemingly harmful gene because the protection it offered outweighed the risks. This complexity teaches scientists to approach genetic editing with humility and caution. When they find genes that appear to cause only problems, they study them carefully to understand whether those genes might serve hidden purposes. They look for the evolutionary reasons why harmful genetic variations have persisted in human populations, knowing that evolution rarely keeps genetic instructions that serve no useful function. Some of the most exciting genetic editing research focuses on variations that evolution is still in the process of testing. Scientists can identify genetic changes that have appeared recently in human history and seem to provide advantages, but haven't yet had time to spread widely through populations. These emerging beneficial mutations represent evolution's current experiments in human genetic improvement. For example, some people carry genetic variations that make them naturally resistant to HIV infection, heart disease, or Alzheimer's disease. These protective variations are still rare because they appeared relatively recently in evolutionary terms. Genetic editing could help spread these natural innovations more quickly, giving more people access to protection that evolution has already begun to develop. The dance between nature and intention becomes most delicate when scientists consider modifications that go beyond existing human genetic variation. Creating genetic changes that have never occurred naturally means venturing into territory that evolution has not yet explored. These modifications might provide wonderful benefits, but they also carry greater uncertainty because they lack the testing that natural selection provides over many generations. Some researchers argue that human genetic editing should stay within the boundaries of natural human variation, using scientific techniques to distribute beneficial genes that already exist rather than creating entirely new ones. This approach would harness the power of genetic editing while respecting the wisdom of evolutionary testing. Others believe that human intention can sometimes see beneficial possibilities that random evolution might take too long to discover. They point out that evolution works slowly and sometimes gets trapped in local solutions that are good enough to survive but not optimal for human flourishing. Intelligent genetic design might create improvements that evolution would eventually discover but that humans need sooner. The most thoughtful scientists seek a middle path that combines respect for evolutionary wisdom with careful innovation. They study natural genetic variations extensively before attempting to modify them. They test their modifications in laboratory systems that mimic the complexity of natural selection. They proceed slowly, allowing each change to be thoroughly understood before moving to the next. This collaborative approach between human intention and natural selection may represent the future of genetic editing. Rather than replacing evolution with genetic engineering, scientists work as partners with evolutionary processes, accelerating beneficial changes while respecting the complex systems that have guided life for billions of years. In laboratories around the world, researchers study the genetic variations that make some people naturally resistant to diseases, naturally gifted with exceptional abilities, or naturally blessed with longevity. They seek to understand how these beneficial traits work so they can share them more broadly through genetic editing. This partnership between human wisdom and evolutionary testing creates possibilities that neither could achieve alone. Evolution provides the vast library of genetic solutions that have been tested over deep time. Human science provides the ability to read that library, understand its contents, and distribute its wisdom more intentionally and equitably. Tonight, as you rest in the quiet darkness, feel the ancient genetic wisdom flowing through your cells. Feel the genetic instructions that have been refined by countless generations of testing and selection. Feel the variations that make you unique, part of evolution's ongoing experiment in human possibility. But consider also the gentle hand of human intention, learning to work with these natural patterns rather than against them, seeking not to replace evolution's wisdom but to fulfill its deepest purposes with greater care and understanding. As this dance between nature and intention continues to unfold, we find ourselves approaching the deepest questions of all, not just what we can do with genetic editing, but what we should do, and how we can rest peacefully with the uncertainties that remain. In the soft twilight between waking and sleep, there exists a peaceful place where questions float like gentle clouds, requiring no immediate answers. Tonight, as our journey through the world of genetic editing draws to a close, we rest in this quiet space, holding the wonder of unanswered questions without the urgency to solve them all at once. Throughout our exploration, we have encountered mysteries that science is only beginning to understand. We have learned about molecular scissors that can edit the letters of life with unprecedented precision. We have discovered how 3 children entered the world carrying modified genes, opening doorways to futures we are still learning to imagine. We have seen how genetic variations create the beautiful diversity of human minds and bodies, each one a unique experiment in the possibilities of consciousness. Yet for every question our journey has illuminated, new questions have emerged like stars appearing in the darkening sky. How do we balance the healing potential of genetic editing with respect for human diversity? When does correcting genetic differences become inappropriate attempts to eliminate natural variation? Who should make decisions about genetic modifications that will echo through generations not yet born? These questions feel heavy in daylight, when the mind demands definitive answers and clear moral boundaries. But here in the gentle darkness of approaching sleep, they transform into something different. They become invitations to wonder rather than problems to be solved. They remind us that the most profound aspects of human existence have always lived in the spaces between certainty and mystery. Consider the question of genetic enhancement. Science is revealing how genetic variations influence intelligence, creativity, physical strength, and emotional resilience. As our understanding grows more precise, the possibility of editing genes to enhance human capabilities moves from science fiction toward potential reality. Yet this possibility brings no easy answers about what we should do with such power. Some people feel excitement at the prospect of reducing genetic suffering and expanding human potential. They imagine children born free from diseases that have plagued their families for generations. They envision enhanced minds capable of solving problems that current human intelligence cannot grasp. They see genetic editing as the next step in human evolution, guided by wisdom rather than left to random chance. Others feel deep concern about the same possibilities. They worry about creating new forms of inequality between those who can access genetic enhancements and those who cannot. They question whether human wisdom is sufficient to guide changes that will affect all future generations. They value the diversity of human experience, including forms of neurodivergence that others might seek to edit away. Both perspectives contain wisdom. Both arise from genuine care for human well-being and flourishing. The tension between them cannot be resolved through more scientific data alone. It requires ongoing conversations that bring together different values, experiences, and visions of what human life should become. As you rest tonight, you can release the burden of needing to choose sides in these complex debates. You can hold space for multiple truths to coexist. You can appreciate both the promise and the concerns that genetic editing raises without feeling compelled to resolve every contradiction immediately. This ability to rest in uncertainty is itself a profound human capacity. Unlike computers that require definitive inputs to generate outputs, human consciousness can hold contradictory possibilities in creative tension. We can simultaneously hope for scientific breakthroughs and maintain healthy skepticism about technological solutions. We can value both innovation and tradition, both change and continuity. The children who will grow up with genetic editing as a normal part of medical care will inherit both the benefits and the responsibilities of this technology. They will face choices about their own genetic modifications and those of their children that no generation before them has ever encountered. Yet they will also inherit the accumulated wisdom of all the conversations happening now about how to use this power thoughtfully and compassionately. Perhaps the most important gift we can give to these future generations is not definitive answers about genetic editing, but rather the capacity to continue asking good questions. They will need the ability to weigh competing values, to consider long-term consequences, and to change course when new information suggests better approaches. They will need scientists who pursue knowledge while remaining humble about the limits of human understanding. They will need ethicists who can navigate complex moral terrain without becoming paralyzed by uncertainty. They will need communities that can have difficult conversations about fundamental questions while maintaining respect for different perspectives. Most importantly, they will need the wisdom to remember that genetic editing, however powerful, is only one aspect of what makes human life meaningful and beautiful. The love between parents and children, the bonds of friendship and community, the capacity for wonder and creativity, the ability to find meaning in both joy and suffering, these essential elements of human experience cannot be programmed through genetic modifications. Your own genetic code, written over millions of years of evolutionary testing, contains both remarkable gifts and inevitable limitations. You carry genes that predispose you to certain strengths and vulnerabilities. You inherited patterns of genetic variation that influence how you think, feel, and interact with the world. Yet you are so much more than the sum of your genetic parts. You are the product of countless influences beyond genetics, the love you have received and given, the experiences that have shaped your perspective, the choices you have made in response to life's challenges and opportunities. You are both the inheritor of ancient genetic wisdom and the author of your own unique story. As sleep draws you into its gentle embrace, feel the mystery and wonder of your own existence. Feel the ancient genetic instructions working quietly in your cells, maintaining the complex chemistry of life while you rest. Feel also the aspects of your being that transcend genetics, your capacity for love, your ability to appreciate beauty, your power to make choices that reflect your deepest values. Tomorrow will bring new discoveries about genetic editing and new questions about how to use this knowledge wisely. But tonight, you can rest in the beautiful complexity of being human, knowing that some of life's deepest truths will always live in the gentle space between questions and answers, between knowing and wondering, between science and mystery. In this peaceful uncertainty, you find not confusion but profound comfort, not anxiety but deep rest.